Good day, everyone, especially to my classmates in the subject and to our dear professor, Ma'am Maribit B. Laron, who are watching this video presentation. My name is Richie Panes, presenting this queuing theory part 2. As a continuation to the discussion made by Ma'am Jeneline Tamayo about queuing theory, that is all about the foundations, the introductions, and the basic of queuing theory. In this video presentation, I'm going to present the different type of models being used in queuing system and the formulas being used in solving the queuing problems. Then later on, we will do some exercises using one model in the formulas as I discussed later on. There are different models being used in solving the queuing system. The first model, as you can see, the equation, it is being divided into two. On the left column, there are three elements being subdivided by the slash. And then on the right column, there are two elements. The first element on the left column, where M, it stands for the arrival time, which follows a Poisson distribution. Then the next M, it stands for the service time that follows an exponential distribution. The one pertains to the service model, which is single, and then the infinite symbol, as you can see, or as the symbol being denoted, it pertains to the capacity of the system, which is infinite. Then the last column pertains to the Q discipline, which is first come, first serve, or the FCFS. This is the model 1, or the first model. Next model, model 2. As you can see, the only difference between model 1 and this model is the capacity of the system. The in here pertains to the capacity of the system, which is finite. The first model, it is infinite. In this model, the capacity is finite. Next, the third model, or model 3. As you can see again, the difference between the previous two models is the Q discipline. In this model, the Q discipline 0 pertains to service in random order. Okay? The fourth one, as you can notice again, it is under the service time that differs from the previous three models. In this model, the service time follows a constant distribution or is deterministic. Okay? The fifth model, again, it is same with the fourth model that the service time differs to the previous 1 to 3 models. G here pertains to the service time follows a general distribution or arbitrary distribution. Okay? Sixth model. Same thing with the fifth and the fourth model. It is the service time that differs from the previous 1 to 3 models. E sub key here pertains to the service time that follows Erlang distribution with key phases. Okay? Next, the seventh model. Now, as you can see, it is in the service model that differs from the previous 1 to 6 models. In this model, the service model is multiple, whereas the 1 to 6 model or the service model is single. Then, lastly, the 8th model. As you can see, here in the 8th model, the service model is multiple, but the capacity of the system is finite. To solve the 8 models, here we need to understand the difference between the arrival time, the service model, the system capacity, and the queuing discipline. On the first model, the arrival time pertains or follows the Poisson distribution, then the service time, the M, follows the exponential distribution with service model as single or one, then the capacity of the system is infinite and the queuing discipline is first come, first serve basis. The second model, it differs to the first model with the system capacity, which is finite. Then the third model, it differs to the one and second model under the queuing discipline, zero, which is service and random order. The fourth model, at this portion, at this junction, it is the service time that it differs from the previous 1 to 3 models, which is D means deterministic. On the fifth model, again, it differs with the service time, which G pertains to general or arbitrary. On the sixth model, again, it differs to the service time E, which means Erlang distribution. Then the seventh model differs from 1 to 6 model under the service model, where key denotes multiple service model. Then the eighth model is a combination of the service model having a multiple service model and the capacity of the system being finite. That is the summary of the 8 models being used in solving queuing, in presenting or solving queuing system. Though there are other queuing models being presented by different authors and researchers, but it means the same. Now let's go to the formulas being used in solving the different type of queuing problems. We need to know the utilization factor or the traffic intensity or the utilization parameter or the busy period. To solve this, we need to have this formula. P is equals this symbol divided by this symbol, where the numerator symbol is the mean arrival rate and the denominator symbol is the mean service rate. Please take note that in a single server model, it should be that the mean service rate is greater than the mean arrival rate. Okay? Please take note on that. Next formula. In determining the probability that exactly 0 units are in the system, we're going to use this formula. P sub 0 is equivalent to 1 minus the result between mean arrival rate being divided by mean service rate. Next, in determining the probability that exactly n units in the system, we're going to use this formula. P sub n is equals to P sub 0 multiplied by mean arrival rate divided by mean service rate. The result is being raised to the power of n. Next, in determining probability that n or more units in the system, we are going to use this formula. P sub n or r or more is equals to mean arrival rate being divided by mean service rate, then raised to the power of n. More than n means n should be n plus 1. Okay? Please remember that. Next, expected number of units in queue or the queue length. The formula will be L sub q is equals to mean arrival rate being raised to the power of 2 divided by the result of mean service rate multiplied by the result of mean service rate minus mean arrival rate. Next, expected waiting time in the queue. The formula will be W sub q is equals to L sub q over mean arrival rate. Next, expected number of units in the system. The formula will be L is equals to L sub Q plus mean service arrival rate divided by the mean service rate. Next, expected waiting time in the system. The formula will be W is equals to W sub Q plus 1 divided by mean service rate. Next, expected number of units in queue from time to time. The formula will be D is equals to mean service rate being divided by the result of mean service rate minus mean arrival rate. Next, in determining the probability that an arrival will have to wait in the system, the formula will be P sub R0 is equals to 1 minus P sub 0. Next, probability that an arrival will have to wait in the queue more than W, where W is greater than 0 or the waiting time in the queue. The formula will be P sub R0 is equals to mean arrival rate being divided by mean service rate multiplied by this constant E, which is being raised to the power of mean arrival rate minus mean service rate multiplied by the W, or the waiting time. Next, probability that an arrival will have to wait more than V, where V is greater than 0, waiting time or waiting time in the system. The formula will be P sub R0 is equals to E being raised to the power of the result of mean arrival rate minus mean service rate multiplied by V, or the waiting time in the system. Next, probability that an arrival will not have to wait in the queue for service. The formula will be P sub R0 is equals to P sub 0. Now, let's go to the application. I hope you learned something from the models and the formulas. In this application, we will going to use model 1, which is aim. The first M here stands for the arrival time that follows a Poisson distribution. Then the next M pertains to the service time that follows an exponential distribution, and have our single model service, and then with a capacity of the system that is infinite, and the Q discipline is first come first serve basis. So here is the scenario. Arrivals at a telephone booth are considered to be Poisson at an average time of 8 minutes between our arrival and the next. The length of the phone call is distributed exponentially with a mean of 4 minutes. Based on the scenario, we need to determine the following. First, expected fraction of the day that the phone will be in use. Next, expected number of units in the queue. Next, expected waiting time in the queue. Next, expected number of units in the system. Next, expected waiting time in the system. Next, expected number of units in queue from time to time. Next, what is the probability that an arrival will have to wait in queue for service? Next, what is the probability that exactly 3 units are in the system? Next, what is the probability that an arrival will not have to wait in queue for service? Next, what is the probability that there are 3 or more units in the system? Next, what is the probability that an arrival will have to wait more than 6 minutes in queue for service? Next, what is the probability that more than 5 units in the system? And lastly, what is the probability that an arrival will have to wait more than 8 minutes in the system? So the problem, prior to solving the questions from A to M, we need first to know what is the mean arrival rate and the mean service rate. So now, what is our mean arrival rate and mean service rate? Our mean arrival rate is equivalent to 7.5 per hour, or as the scenario says that the arrivals at the telephone booth are considered to be poisoned at an average time of 8 minutes between our arrival and the next. So in 1 hour, there are 7.5 arrivals. Our mean service rate is equivalent to 15 per hour. As this problem also says, the length of the phone call is distributed exponentially with a mean of 4 minutes, meaning in 1 hour there are 15 phone calls. So that is our mean arrival rate and mean service rate. Now, we're ready to solve the questions. The first one, expected fraction of the day that the phone will be used. We're going to use this formula, which is mean arrival rate divided by mean service rate. Fill in 7.5 divided by 15, which is equivalent to 0.5 or 50%. So 50% is the expected fraction of the day that the phone will be in use. So it is half day. Next, letter B. Expected number of units in the queue. We're going to use this formula. L sub q is equals to mean arrival rate being raised to the power of 2 divided by the result on mean service rate multiplied by the result on mean service rate minus mean arrival rate. Fill in. So the formula will be 7.5 raised to the power of 2 divided by 15 minus 15 times 15 minus 7.5. It is equivalent to 0.5 units per son. Okay. Okay. Letter C. What is the expected waiting time in the queue? We're going to use this formula. W sub q is equals to L sub q divided by main arrival rate. We already computed the L sub q from letter B. So fill in, our formula will be 0.5 divided by 7.5 is equals to 0.066 hours. This is our expected waiting time in the queue. Next, letter D, expected number of units in the system. We're going to use this formula. L is equals to L sub q plus mean arrival rate divided by mean service rate. So we have already computed our L sub q on letter C, which is 0.066. So fill in. 0.5, sorry. So fill in. The result will be 1 person. So that is our expected number of units in the system, which is equivalent to 1 person. Next, letter E. Expected waiting time in the system. Our formula will be W is equals to WQ sub Q plus 1 over mean arrival rate. Fill in. We already computed WQ under letter C. It is 0.066 plus 1 over 15. The result is 0.133. So this is the expected waiting time in the system, which is equivalent to 13.3%. Next, letter F. Expected number of units in queue from time to time. Our formula will be D is equals to mean service rate being divided by the result of mean service rate being deducted by the mean arrival rate. Fill in. So 15 divided by 15 minus 7.5 is equivalent to 2 persons. So our expected number of units in queue from time to time is 2 persons. Next, letter G. What is the probability that an arrival will have to wait in queue for service? We're going to use this formula. P sub R0 is equals to 1 minus P0. Fill in, or we all know that P sub 0 is equals to 1 minus mean arrival rate being divided by mean service rate. So the formula will be 1 minus the result of 1 minus 7.5 divided by 15, which is equivalent to 0.5. That is the probability that an arrival will have to wait in queue for service, 50%. Next, what is the probability that exactly 3 units are in the system? We're going to use this formula. P sub n is equals to P sub 0 multiplied by mean arrival rate being divided by mean service rate, which the result of is being raised to the power of n. So fill in 0.5 multiplied by 0.5 raised to the power of 3. That is 0.0625 or 6.25%. The probability that exactly 3 units are in system. Next, what is the probability that an arrival will not have to wait in queue for service? We're going to use this formula. P sub R0 is equals to P0, which is P0 is equals to 1 minus the mean arrival rate being divided by mean service rate, which is equivalent to 1 minus 7.5 over 15, resulted to zero point 0.5 or 50%. So there are 50% that the probability that an arrival will not have to wait in queue for service. Next, letter G. What is the probability that there are 3 or more units in the system? Please take note, 3 or more. As I discussed previously, the N3 pertains to N plus 3 or more. 3 or more, exactly 3 or more. So we're going to use this formula. P sub N or more is equals to mean arrival rate divided by mean service rate raised to the power of n. Fill in, we have 7.5 divided by 15 raised to the power of 3. We have 0.125 or 12.5%. That is the probability that there are 3 or more units in the system. Next, letter T. What is the probability that an arrival will have to wait more than 6 minutes in queue for service? We're going to use this formula. P sub R0 is equals to mean arrival rate being divided by mean service rate multiplied by the constant E, which is being raised to the power of the result on mean arrival rate minus mean service rate multiplied by the waiting time. So fill in. W here is equivalent to 6 minutes or 6 over 60 hours. So the formula will be 7.5 divided by 15 multiplied by E raised to the power of 7.5 minus 15 times 6 over 60, which resulted to 0.236 or 23.6%. Please take note that in solving this formula, we need to use a scientific calculator. So the probability that an arrival will have to wait more than 6 minutes in queue for services is 23.6%. Next, letter L. What is the probability that more than 5 units in the system? So our n here should be more than 5. So it should be n plus 1. So we're going to use this formula. P sub R0 is equals to mean arrival rate being divided by mean service rate raised to the power of n. Fill in 7.5 divided by 15 raised to the power of 5 plus 1, which is 6. It is equivalent to 0.015 or 1.5%, the probability that more than 5 units in the system. And lastly, letter M. What is the probability that an arrival will have to wait more than 8 minutes in the system? We're going to use this formula. P sub R0 is equals to E being raised to the power of the result on a mean arrival rate minus mean service rate multiplied by V, or the waiting time. Our V here is equivalent to 8 over 60 hours. So the formula will be E raised to the power of 7.5 minus 15 multiplied by 8 over 60, which is equivalent to 0.367 or 36.7%. Again, we need to use a scientific calculator in solving this formula. So the probability that an arrival will have to wait more than 8 minutes in the system is 36.7%. That's all, and thank you so much for watching. I hope you learned something. Again, this is Roy Richie Panes. Thank you once again.